Hi kids, happy Tuesday. I hope everybody is doing well. I can't put into words how much I miss all of you, and I can't wait until we're all back together. In the meantime, we're going to start with where we left off. My plan is to follow our plan, to continue to do the study logs and the same homework and classwork assignments. We're just going to do them remotely. Every day I'm going to be available for a Google Meet. I'd like you all to make sure that you go on Google Classroom today and kind of read what I posted over the weekend. All right, so let's get started. We're going to start with section D of the If You See This, Think This. I'd like to get D and E done today. This will be my 5th recording attempt, so it looks like it'll take me about 15 minutes of video. So I apologize. You're going to have to listen to me for 15 straight minutes. So whenever we do this on Tuesday, I really would like you to go back to the beginning of this packet and review what we've already talked about. We've talked about the pre-calculus type problems, the limit problems, ignore BC, and the derivatives, differentiability, and tangent line rules. And so what I want you to get in the habit of thinking is when you see problems, I want you to see these words, and this is what you got to do. Okay, so for applications of derivatives. The first section is finding critical values of f of x. So if you're asked to find critical values of f of x, you got to identify what a critical value is. And critical values are where f prime of x equals 0 or d(n)e. Okay, and we use these critical values for determining where a function is increasing or decreasing, or where any relative and extrema happen. So for D1, it really is exactly what you're going to do for D2 and D3. You're going to find out where the slope equals 0 for both of them. And then you're going to do what we call a candidates test, which is that sign test. So let's say that we found the value is some x. And then you're going to plug in values to the left and the right of the point you found. Now, a lot of times there's multiple points, but for this example, we're just going to give that there's one. And so you would plug a number in that is a little bit lower than x, and let's say it was positive. And that would mean that everywhere below x, the function is increasing. And so if we put one into the left side, a number a little bit larger than x, and it's negative, that means it was decreasing on that interval from x to wherever. This also helps with relative extrema because if we know that a graph is increasing and then decreasing, we know it went up and then went down, that makes this point at x a relative maximum. Now obviously it could go the other way and you would see, I don't know, negative then positive, and it would make it a minimum. All right, for D4, we are going to find inflection points, your favorite points of inflection. This is going to be where f double prime of x equals 0. And so for inflection points, we're still going to make the sign chart and see how the graph is behaving. We know that this is where concavity changes. So if it's positive on the left, that means it's concave up, like all of your smiles. And if it's negative, it's concave down. There's a sad face. All right. Part D5 says to find absolute maximums or minimums. We know that absolute maximums and minimums happen where f prime of x equals 0 or endpoints. And a lot of times on the free response questions, they're going to ask for the maximum value or the minimum value, and so you have to check where the slope is 0 and where the endpoints are on your interval. Again, you would do a candidates test to see what's going on there, and most of the time you'll be given a derivative and you got to integrate. Okay, so finding the range of f of x. This is just end behavior. And so this throws us back a little bit to limits, right? So you're going to look at the limit as x approaches positive and negative infinity of f of x. If you have to find the range on a set interval, right, depending on what they give you, you may have to integrate a derivative. But what you want to do is you want to find out what f of a is and f of b is. And then anywhere that we would see a relative max or min. So we're going to take f prime of x again and equal it to 0. See what that value turns out to be. Okay. What are we on? D8 and 9? For D8 and 9, the reason we're going to put those two together is because MVT is, I'm sure you all know this, AROC equals IROC. Now the conditions we need to meet is differentiability, right? Let's see if I can spell this right. Probably not. I'm really sorry. Things don't change. I can't spell. We need to make sure it's differentiable, because if it's differentiable, then it's continuous. But both of those things have to be true for MVT. Okay, and then what you'd be asked to do is to show that there's some C value where this is true, where the AROC equals the IROC. In the case of Rolle's theorem, we're looking at the slope would have been 0, right? Which would make f of A have to equal f of B. So it's a slight difference on it, but again, you still want to show that it's continuous and it's differentiable, and that if f of A equals f of B, there's somewhere that f prime of C equals 0. D10. Oops, let me change the color. I feel like Sal Khan. Given a graph of f prime, determine intervals where f of x is increasing or decreasing. So again, you're just going to make a sign chart, right? So if they give you the graph of f prime of x, just look for where f prime of x equals 0 and make your sign chart. That's pretty straightforward. I feel like that should have been higher up on this paper. All right, D11. D11, determine where the linear approximation, oh, those are fun words, for f of x plus a little bit is an overestimate or an underestimate. So there's two parts here. A linear approximation involves figuring out what f prime of x sub 1 is, writing a tangent line, and then plugging in x sub 1 plus a for x in your tangent line. So if you have the equation y equals m times x minus x sub 1 plus y sub 1, you would plug in this value for here and then get your y value of your new point. The second part of that is whether it's an underestimate or an overestimate. This is where we're going to use f double prime of x equaling 0. Because once we know the concavity, then we can determine whether the tangent line is sitting above it or sitting below it. All right, D12. Find the intervals where the slope of f of x is increasing. Much to your luck, this was something that was tested years ago and is really not tested anymore. So you would find f double prime of x, which is the derivative of f prime. Find the critical values, right? So the critical values would be where this equals 0, and then make a sign chart. And so wherever f double prime of x is positive, it's increasing. D13, find the minimum slope on a to b. So you're going to find the derivative of f prime again. You're going to find the critical values of f double prime and make a sign chart. And the values where it's going to switch from negative to positive are going to be potential locations for a minimum slope. Evaluate f prime at those values, and then you'll be able to find that. So let me write that down. F double prime of x equals 0. Sign chart again. This is a very tiny box for a lot of writing. And then these are potential minimums. But what you're looking for is where it was decreasing and then increasing. After you get that, you plug those values in and see which one is the minimum. All right, E1. This is where it gets a little bit easier for today. Approximate a to b of f of x dx using left Riemann sums with n triangles. So for E1 and E2, we are going to be consistent with, we've got the change in x over n in order to find our area. The n being the number of intervals we have. And that's consistent with actually the next three. So midpoint, change in x over n, and the trapezoid. So we're all four. That's good. I'm sorry how loud the pen's clicking. I can only imagine that you're hearing it. We're going to take the change of x, and so for a left-hand sum, we're going to add leftmost points. So really, this is going to leave out f of b. And for a right Riemann sum, we're going to add rightmost points, leaving off f of a. And so you just add them up and multiply them by the change in x over n, and that'll give you the left and the right Riemann sum. The midpoint sum is a little bit trickier. This is usually done from a table. And so if you're asked to do from a table, typically what you need to do is be sure to only use the values that you're given. You can't make up values. So you will only be able to find so many intervals, right? But we're going to add the numbers in the middle of our intervals. And that's easier to understand in practice than it is to like write a definition. Middle of interval. And I think the directions, the example that the directions give you is it says if you're given 7 points, you can only calculate 3 midpoint sums. For the trapezoidal rule, we have to use our area of a trapezoid formula, which is 1/2 the height times our bases summed. And so we will see this as our height right here times 1/2 from our trapezoid formula times the sum of our bases. Now sometimes the bases double, sometimes you got to do these all individually. Okay, now the easy stuff. E5, what happens when the bounds are switched? When our lower number happens to be at the top of our integrand and our higher number happens to be at the bottom, we just switch it. So we got negative a to b of f of x dx. That's a nice one. E6 shows up a lot. I think on the 2 free response questions I assigned for homework, both of them entailed some sort of integrating to a variable. When we integrate to a variable, that is known as the fundamental theorem of calculus. And so what that means is really you're just going to wind up plugging in to an accumulation formula, right? It's the area under the function from some number a to an ending variable of x. And as we get further down, you'll see what that looks like as a derivative. The end result would be capital F of x minus f of a. And usually they tell you what f of a is, so then that'll give you the end interval. If we're integrating a function and we want to find the integral of the function plus some constant, we can separate these. We can integrate f of x from a to b. And then in this case, we would add to it k times b minus a. And that's an old properties of integration rule. It can be useful, but I think a lot of times now you're just kind of adding an x to k and then integrating as normal. If you were given the value of f of a where the antiderivative of f is f, find f of b. This is again, we see that idea of initial condition. Because if we go back to the fundamental theorem of calculus, I'm going to write it down here actually at the bottom of the page. The fundamental theorem of calculus says if we integrate from a to b, lowercase f of x dx, it equals some f of b minus f of a. Well, if you know the initial condition, the f of a, what you can do is you can add it to this side, and it becomes your initial condition plus whatever this integral turns out to be. And so that's how we use this rule to find f of b. So as promised, the last 2 rules are, again, the fundamental theorem of calculus, but now it's the second fundamental theorem of calculus, and this is where we're taking the derivative of an integral. As we know, derivatives and integrals are opposite operations, and so what you would most likely expect is for this to cancel out and this to cancel out. But what you have to remember is that f of x substitutes in. That should be a capital F. Let me erase that. Switching colors and erasing like Salcon. Plus some value of C. That's how this would turn out when you take the derivative. Oh no, I'm wrong. I'm sorry. Let me erase that. I hope you didn't write it. Let me clarify that again. I kind of just forgot what we're doing. Take the derivative of the integral, you get f of x. Right, and so there is no plus c because you didn't integrate. And if you take the derivative of a constant, it would go away anyway. All right, my apologies. E10, and I promise not to mess this up. Now what you're doing is plugging in a function. And so you would get f of g of x, much like you did in the example above. But this has got to be times whatever the derivative of g is, which is chain rule. Okay, kids, one mess up and, you know, lots of color later. I think we're done for today. If you have any questions for me, please feel free to contact me via Remind. I will be on Google Meet from 9 to 10:30, I believe. I'll send you the class code in the morning. I look forward to seeing all of you. I hope you're staying well and in contact with each other. I definitely believe in our ability, and I don't have any worries about how well you're going to do when we get back. All right, take care.